Hello, my name is Timo Giese from Function Bay GmbH, and together with my colleagues Davide Marano from GearLab Italy and Simon Schneider from the University of Applied Science in Ulm, we want to talk about the NVH simulation of an automotive e-axle. After a short introduction, we have a general chapter about the order analysis and what response we theoretically expect from our system. We will walk through the main components and evaluate the different modeling methods we have in the multi-body simulation. The next chapter will be the optimization of gears, where we will compare a standard and a high contact ratio gear. After this, we focus on the multi-body simulation, where we want to talk about the dynamic response and the influence of the housing. In the end, we will compare several simulation results. So let's start.
The sound of vehicles' electric axles is the result of the high-frequency whining noise generated by electromagnetic forces of motors, gear meshing frequencies of transmissions, bearing frequencies, as well as the high-frequency noise generated by the DC-AC converters. The NVH behavior of an electric axle is not comparable to a conventional vehicle powertrain. In fact, an internal combustion engine is generally characterized by lower orders with a higher sound pressure level, thus masking the higher orders from the transmission, while an e-axle is generally characterized by higher orders with a lower sound pressure level. However, the high-frequency noise of the motor and the transmission is subjectively quite annoying.
Okay, let's have an ear on some examples. Here we have a front drive unit while speed up. We can directly hear the high frequency noise. Here we have another example, but we have to mention in this case we have bad bearing behavior. Please keep this in mind. In this example you can directly hear the rippling noise coming from the failure. The simulation is always an approximation to reality. In multi-body simulations there are different imaging variants for different components. For example, bodies can be integrated as a classical rigid body, finite element structure or reduced flex body. Furthermore, there are many different modeling types for forces and contacts. In the following we'll go into the essential components, housing, bearings and gears, to have a look on what level of detail we need for the NVH simulation of an automotive e-axle. The housing serves as a resonator and its flexibility has also influences to the positioning of the components, so a rigid body is not suitable for our task. To provide flexibility, this rigid body can be meshed and be integrated into the simulation as finite element structure. The quality of the simulation results is ideal here, as even geometrical and material non-linearities can be included into the simulation. The problem is the simulation time, as on each simulation step the full degrees of freedom of the finite element structure has to be solved. So this approach is only suitable for small structure and 2D meshes. To speed up the simulation, the finite element structure can be transformed into the modal space. The quality of the results is depending on the number of eigenmodes used in the simulation. The difference between the ideal finite element result and its derivative results is called the truncational error. For our NVH simulation, we use the reduced flex body approach.
Vibrations related to the bearings can be either tonal or broadband. Tonal vibrations in new bearings are generally caused by production imperfections, including but not limited to the cases when the stiffness of both inner and outer rings is not ideal and they get ovalized due to the clamping for grinding. Broadband vibrations originate from the defects of raceways and rolling element imperfections. A smooth operation is thus expected when the bearings are new. The SKF company has published a comprehensive analysis of bearing damage and failure modes and a guide to the interpretation of vibration signals. In this slide, the calculation of main bearing defect frequencies is presented as a function of the ball bearing dimensions and other bearing geometric parameters.
Bearings as one of the main machine elements provide static and dynamic compliance, but they can also excite the system. There are many different ways how a bearing can be included into multi-body simulation. There are joints, linear bushings, matrix forces, non-linear bushings, higher force elements, rigid contact models, and finite element contact models. One criteria is the simulation time. This is very high on FEM-based models, so the simulations are suitable for component level, but too inefficient for system integration. Another point is the simulation accuracy. Where a joint is a too high simplification for an NVH analysis, as it only provides infinite stiffness. For the other bearings, let's make a simple test for the comparison. We use a 6004 bearing and fix the outer ring to the ground, and we apply a displacement to the inner ring. As a result, we have a look on the reaction forces to the ground. The remaining bearings are the linear bushing, where the results were plotted in yellow, the matrix force in green, a non-linear bushing in gray, an MBS contact model in red, and a higher force element plotted in black. The higher force element is validated from the manufacturer and is now our reference. As we apply an actual displacement, we can see that the matrix force and the linear bushing don't cover the actual clearance, as they are linear models. If we also add a radial and a rotational displacement, we can see that also the non-linear bushing is not aligned anymore, as this model is not covering the cross effects from one axis to another. So we can see that just the MBS contact model is following the reference. Another huge point is the data availability, which is quite bad for nearly all simulation approaches. As for a good simulation result, we need the knowledge of the inner geometry, which is usually not provided by the bearing manufacturer. But there is a way how the inner geometry can be approximated using the load ratings, which we provided as a standard value. As this is an approximation, it's essential to check the results and adjust them if necessary, especially with respect to the overrolling frequencies. But in general, with the help of this approximation, the data availability is okay for our task. In our model, we use an MBS contact model based on an approximation, as this gives us the most flexibility in our system.
The spectrum of any electric axle shows a range of frequencies related to the gear meshing frequency. The fundamental gear meshing frequency is calculated as the product of the number of teeth of a pinion and its respective shaft frequency. The amplitude of the gear meshing frequency is usually related to the transmitted load, thus the vibration analysis of the axle should be conducted at the maximum power. Sidebends around the gear meshing frequency are quite common due to gear faults such as wear, defects, misalignments, and eccentricity.
Gears are the main transmission elements in our model and can excite vibrations due to the tooth meshing. Once again, we have different modeling approaches, as there are analytical contact models, surface contact models, finite element contact models, co-simulations to a gear expert program, as also a meta-model approach. To have a look which model is the best for us, let's first have a look on the finite element result of a gear contact. Concerning on the stress recovery, we can see that we need to cover mainly three effects: the local flattening, the tooth bending, and the deformation of the gear body. So let's compare the different modeling types. As a note, the meta model is subtracted out of the static modeling, so we don't need to co-simulate with the static solver in this comparison. As a test, we use two meshing gears with only 2 degrees of freedom. The bigger wheel is treated with a zero motion while loading a torque. Then we rotate a few degrees to see the tooth meshing. We observe the reaction forces in radial Y direction of the revolute joints. First, we have a look on the most general approach, the general surface contact. And we can see that during the contact changes we have some noise. This is caused due to discretization these contacts are using. These effects can be reduced and prevented by good settings. Nevertheless, the model has the potential to excite the system by numerical effects. The problem here is that if they occur, it's hard to separate the numerical noise from the one we want to observe with our models. These models cover the local flattening, but we don't get effects out of the tooth bending and the body deformation. Next is an involute contact. As these contacts are analytical models, they avoid excitation due to surface discretization. During the simulation, we can directly see the shocks where the gear contact is changing. These models usually only cover the local deformation. The most time-consuming simulation is the next. We take the two gear bodies and transform them into the finite element model. As we can see, the results are quite noisy, as this contact was not optimized. The main problem finite element-based contact models is that we need a very dense mesh in the contact area. But as we were interested in simulations covering a long transient range, the contact area is not just on one or two T's. Another point against the finite element-based gear analysis is that the contact is discretized by the mesh, where the microgeometry of the gear body might be lost. But this model covers all effects we want to see in our simulation, as we have the local flattening, tooth deformation and the deflection of the gear body. As we have a closer look on the area between the noise, we can assume that the gear has a more complex behavior than we have observed in the analytical contact model. Next, we have a look on the meta model, which is based on a static contact model coming from Keyswift. During the rollover, we can see that due to the tooth bending, we get the contact shocks, which can be seen in the nonlinearity of the line of action of the gear meshing. As the Keyswift calculation covers the local deformation, the tooth and wheel body deformation, it's also included in our meta model. As a minimum set of degrees of freedom, we have the rotational angle and the penetration. Additionally, the distance error, the axial offset, as well as twist and tilt can be included. Here we can see a force representation of a meta model covering the 6 reaction forces. The simulation time of a meta model is very fast, but depending on the dimensions covered in the pre-simulation, time can vary from several seconds to a few hours in the pre-simulation. In our models, we use the meta model approach based on the Keyswift pre-simulation, as this guarantees the best simulation results.
I will now shortly introduce the design and optimization of gears for NVH by using Keyswift. We will start by sizing the center distance and phase width for each gear stage. Then we will have to find out the optimal macrogeometry of the meshing, module, pressure angle, helix angle, and so on. As we will use case-hardened gears for the E-axle, we will probably have some distortion after hardening process. So we may also design a grinding stock for hard finishing process, and in order to avoid grinding notches, a proper sizing of the cutter must be performed. Then we will perform the calculation of the system deformations, and these will influence the gear contact pattern. So in order to optimize the gear contact pattern along the flank width, we will design some micro modifications such as helix angle and croning. After we optimize the contact pattern, we can face the NVH optimization of the gears by means of profile modifications. To fix the main parameters as center distance and tooth width of the transmission, that will of course influence the housing dimensions. As input we have torque and speed, so the power, the gear ratio, the gear material quality, and so the required safety factors and the required life. The goal of the rough sizing phase is to find out the optimal center distance and phase width in order to define the gearbox dimensions. The choice of the solution strongly depends on the defined targets. Several options are possible. In this study we focused on maximum power density solution. Let's get into fine sizing. The basic idea is to find out the optimal gear macrogeometry by calculating multiple solutions, by fixing some module range, pressure angle range, helix angle range. Maybe we do not want too high helix angle because of axial forces on the bearings. And very important for the NVH, we can fix some target contact ratios. Again, multiple solutions are possible. We can find a solution with high safety factors or low weight, or for example for NVH we choose to have high contact ratio gears to have lower excitation, or we can have the highest efficiency solution. Previously said, we now need to size the grinding stock. This is a quite nice formula provided by Gleason to estimate the grinding stock per flank. If the flank is ground and the root not, a grinding notch will appear in the root area. Due to the notch effect, the root stresses will increase, so in order to avoid the grinding notch, a protuberance cutter should be designed. Among several e-axle concepts, we choose as case study the two-stage cylindrical gearbox. The design and optimization of the transmission was performed in Keyswift. We compared different gear sets. The first one with low contact ratio and the second with high contact ratio. Simulations are carried out for performance improvement evaluation of the high contact ratio gears with respect to the low contact ratio gears regarding the peak-to-peak transmission error, the gear meshing forces and the bearing forces.
Okay, before we now have a deeper look at the transient results, let's focus once again on our model. Our model has now several linear components like housings and shafts, as well as non-linear components as the bearings and the gears. The nonlinearity of the system can easily be seen as we simulate 100% and 10% of our nominal torque and check the under natural frequencies. These eigenfrequency simulations are a good first checker of our system to see if everything is assembled correctly and to get the first informations. So we might check our first rigid modes of our gear train. Here are some modes as an example. Our system behavior is now a combination of the models of the gear train and the free modes of the housing. One question is now, how good is my housing represented by the linearized reduced representation? To evaluate this, let's switch to Simon into the sound lab. He has answered this question on a small example gearbox.
Hi Timo! As you have already mentioned, I am currently examining, among other projects, a small gearbox for its dynamic behavior. In the following, I want to introduce you some first results of this evaluation. The gearbox consists of the housing assembly, 4 gear shafts and 3 gear stages with a total ratio of 83. To determine the dynamic behavior of the transmission housing by an analytical model analysis, the assembly will be meshed in RecurDyn. In addition to the discretization and the material characteristics, the connection between the screw-rod components plays a very important role regarding the eigenvalues and the eigenfrequencies. This interface region is defined by the limiting diameter according to BDI 2230. Therefore, the cover and the housing are merged by the pressure cones of the screws. Further, the mass of each screw is positioned as a mass element at the respective mass center and is connected with the threaded holes via interpolation every 3 elements. For our first validation, we perform also an experimental modal analysis of the housing. With the EMA method, we can determine the modal mass, the modal damping, the eigenvalues and the eigenfrequencies. So, if we compare the analytical and the experimental modal model, we get following Mach matrix. The average Mach value is 91% and the average frequency error is about 0%. For the numerical analysis during a run-up, we simulate the gearbox in RecurDyn in a flexible multi-body simulation based on the results of the correlation and the modal damping gained from the EMA. To evaluate the multi-body simulation, we also examine the real gearbox in our low reflection room during several run-ups. At this experimental method, we measure the surface velocity of the housing and also the rotation speed of the gear shafts. Further, we record the sound pressure at the surface of the structure as well as 1 meter away of the gearbox. Let's have a look at the time domains of the surface velocities between the simulation and the measurement over a complete run-up. As reference, we consider the node at the side of the housing. The velocity plot of the simulation is very similar with the one of the measurement. Both curves show an increase over the time and thus over the speed of rotation. But for a more accurate statement, we have to transform the time signal into the frequency domain. If we compare the numerical and experimental analyzed frequency domains of the velocities, we can recognize the simulation shows similar high peaks at the eigenfrequency as the measurement. For example, around 4 kHz. If we take into account that there are extremely many unknown parameters, the results speak for themselves.
Okay, now finally we come to the point where we want to turn the theory into application, or we want to add a z-axis. So let's make a speed-up simulation on our e-axle going from 0 to 5000 RPMs in 5 seconds at a load of 535 Newton meters. We will place a virtual accelerometer on the housing and we measure the phase normal acceleration for our Campbell diagrams. The sound pressure level calculation is based on a zero-order spherical radiator at a certain distance. That's just an assumption as we don't want to go into the airborne sound calculation right now. But it's quite good for a comparison. The AVIs will show the ERP value with a defined overload, and we also hear the structural borne sound of a representative node set. First, we compare the low contact ratio results with the optimized high contact ratio gears. For the comparison of the sound, I set an equal max peak at the initial time step for all our following simulations. As you can see, the HCR results are much better than the not optimized gears, with a degree of the SPL of about 8 dB. And also the Campbell diagram, you can see directly the difference. That's impressive, but now we face a general problem in our simulations. The results represent the ideal geometry, but this is not what you get in reality. For example, the gears have a certain defined quality level. So what happened if we add a medium production imperfection for such gears into our simulations? I hope you liked our presentation about the NVH simulation of an automotive e-axle. I would be happy to answer your question directly now in the Q&A session. Or if you want to have a discussion more in detail, please visit us at our virtual booth. Thanks and goodbye.